Good morning, everyone. Thanks a lot for attending. This is my first time attending SUMO conference, so I'm really happy to be here. And I'll definitely come next year. So this is the group that I work with for our title, Digital Twin-Aided Municipal Traffic Control. This is the outline of my talk. I'm going to give a statement of the problem and try to state what problem we're trying to solve, some motivation and key challenges, some technologies we use like YOLO and SUMO and Tracy and Python. We kind of group all of those technologies together. We have a traffic throughput optimization algorithm. It's very simple. And I'll talk about the digital twin-aided municipal traffic control system. I'll give some evaluation and some results, some conclusion and some questions. So this is the statement of the problem. It's like we're basically looking at a four-way intersection, and it often suffers from congestion, some network congestion. So the two problems that we're trying to address is that the low throughput, the number of cars that come through the intersection per unit time, and the high average time that it takes the car to move to the intersection. So I think I'm just using the standard definition of throughput here. It's defined as the number of vehicles passing through an intersection per unit time. In our case, it's minutes. And the average time is the time to travel through a specified region. It's not the intersection. It's a little bit larger than the intersection because I'm taking a video of an intersection. So the average time here will be the car that goes from the input of one frame to the output of the video frame. So that's the specified region. And the question is, how can throughput and average travel time be improved and possibly optimized? So I don't think that I need to belabor the point that reducing the travel congestion can help us save money, time, and freight efficiency. That's kind of like economic, and lower emissions. That's environmental, and improve safety and public health. That's kind of social, and enable smart mobility systems. That would be technological. So for these reasons, that's why we want to focus on increasing the throughput. So challenge one is I wanted to extract some traffic volume quickly and automatically from a video that's pointing at an intersection. I'm going to use YOLO to do that. It stands for you only look once, and you could extract the movement of the data where the cars are going. Number two challenge is to optimize the traffic lights reactively based upon volume. To give you the sense, we'll look at the video for X number of minutes, and we'll go through 21 different scenarios. We will extract the traffic pattern that gives us the best throughput, and we'll use that traffic pattern on the next X number of minutes. So it's an iterative process, and that's how we're going to do it. So that's why it's reactive, because I'm taking my optimization from the traffic that passed X number of minutes, and I'm using that for the next X minutes. But our future plans is to use AI to predict what the traffic will look like using frame aggregation. And based upon that prediction, then we'll set the traffic lights to what the traffic we predicted will be. So that'll be, and that's the challenge number 3, is to predict future traffic for proactive control. It's current and future work. So the conclusion is that we need a robust real-time traffic optimization solution. It's urgently needed to address dynamic congestion challenges. Okay, so I think we've just picked a section of the United States randomly because the data was readily available. And that place is Bellevue, Washington. And if you zoom in, this is what the intersection looks like here. And if you zoom in a little bit further, this is a video snapshot of that intersection. So, and that's Northeast 12th Street and 116th Street Avenue Northeast. So this is what it looks like. And this will be analyzing the video at this intersection using YOLO to capture the movements of the cars and their speeds and ID the cars. And then based upon that, we will use SUMO and Tracy to set the traffic lights and calculate the throughput and use the traffic light that has the best throughput to run the next X minutes. I hope I'm giving you a big picture of what it looks like so that when I go to the details, everything will fit, kind of like a puzzle. So as I mentioned, we're using YOLO to do real-time vehicle detection and tracking in the video. SUMO is the open source microscopic traffic simulation, of course. Tracy is the interface for real-time simulation and control within SUMO. And Python is the programming language that we're using to integrate all these three together. So let's see. So SUMO, again, detects the vehicle as a movement of the vehicle. And I'm extracting the static and dynamic data from the video, and I'm putting them into XML files. SUMO with Tracy simulates the traffic on the different traffic light settings, and the optimization traffic settings are used for the next simulation phase. So I'm looking at X minutes, and I will get the throughput, calculate the best traffic condition, traffic light settings, and then I will use that for the next phase. As I mentioned, it's reactive, and you may say this is probably some older technique, but what it does, it gives us a foundation to make some future projections. Like, for example, what we can do is once we look at the current X minutes and get the maximum throughput and the traffic light settings, I have results to show that I will use that again on the first X minutes. Assuming that I know the perfect traffic pattern, you'll see I'll get the optimum results. Assuming I know the best, what the traffic looks like, that will give me the best results. Of course, my results will be a little bit less than that or much less than that, but it will be less than that. That's the theoretical throughput that I can expect. So you'll see those results at the very end. Okay, so here is my traffic throughput optimization algorithm. It's pretty simple. I initialize the traffic light pattern scenarios, and then I consider 4 decision times in minutes. I consider 2, 3, 4, and 6, meaning that I will examine the video for 2 minutes, and then I will calculate the throughputs and pick the traffic light settings that give me the maximum throughput, and I will use that for the next 2 minutes. So I'm using that as 2, 3, 4, and 6. And then step 3, for each of the cycle times, I will run 21 traffic light pattern scenarios, calculate their throughputs and their mean travel times, and I will set the traffic light pattern scenarios to the one that gives the highest throughput. And then I will go to step 2 until the simulation reaches 12 minutes. So I have a 12-minute video. So for example, if I look at the 2-minute decision time scenario, I will run that 6 times. And if I look at the 3-minute, that will run 4 times. This will run 3 times. This will run 2 times. So that is the framework that I'm approached to the problem. So as I mentioned, this is what SUMO is. It's kind of used as a digital twin. The more data that I have for my digital twin, I'm assuming that I can make better decisions, which is a safe assumption. The traffic light modeling and simulation platform is explored. I put all of my static and dynamic data in XML files. The optimization algorithm finds the best traffic light settings by trying various traffic light scenarios. I'm adjusting the length of time for the green, yellow, and red for the 4 different durations. And I'm using CCTV captured data and extract relevant traffic information. So my digital twin will simulate the physical system for real-time decision making. As you know, digital twins are widely used in transportation, manufacturing, and power systems. and it enables persistent optimization by mirroring physical systems with virtual models. So my SUMO serves as the digital twin of the actual physical system. So that's what we call it DiTAT. It stands for Digital Twin Aided Traffic Control. Uses surveillance video to extract real-time video. And I will integrate AI tools such as YOLO, You Only Look Once. That's for detecting the vehicles. And Traffic Simulator SUMO with Tracy to change the traffic lights to optimize the throughput. So I think at this point, sorry for the blurriness here, it gives us a big picture of what the scenario looks like. So these X minutes will be 2, 3, 4, and 6. So if you take the 2-minute scenario, I will look at 2 minutes of video and I will extract the static data and the dynamic data. I will generate the XML files. And then once I look at that 2-minute video, I will set the initial traffic light scenarios, and I will run 21 different scenarios, and I will calculate the maximum throughput, and I will pick that traffic light which calculates which corresponds to the maximum throughput, and I will use that for the next 2 minutes, and then I will do it again. So it's an iterative process. I will use it for 2 minutes and 2 minutes, and I will do it 6 times. Then I will do this for X equals 2, 3, 4, and 6. So that is the big picture. Of course, I have three files for network generation. I have a node file, I have an edge file, and I have a type file. And I use this network command to generate the network file. And this is what the real-time video layout looks like. And this is what the manually generated road layout looks like. There's a slight angle tilt here, but I think for my purposes, I don't find that it makes a bit of difference for the tilt. And this is the dynamic data. This is what it looks like. If you ever use YOLO before, you can see that you can identify the cars, draw boxes around it. You can get the vehicle IDs, the entry and exit zones, their routes, the vehicle type, the speed, departure time, and all of this data is stored in the route file. And this is what my configuration file looks like. I'm combining my static data and my dynamic data. It serves as the main input for the SUMO simulation. It points where the network and route files are. And this is I mentioned this before, I'm using Tracy, Python. It gives me access to the SUMO traffic simulation during simulation for the position and speed. And I'm modifying the traffic lights with Tracy. This is a snapshot this is the green phase for the north-south direction. So this is the north, south, west, east. And this green stands for a car that can turn this direction, that can go straight, and that can go straight here. These 3 greens. And these 3 reds are, I think 6 or 7 reds here, and 3 greens are here. So this is the green phase for the north-south direction. This is the yellow phase for the north-south direction. And this is the red phase for the north-south direction. So I'm using these patterns in the simulation to generate the different traffic scenarios, traffic light scenarios. This is a repeat of the same picture. It's good to show it twice. Just to repeat that, I'm running each of the video analysis for X. This is my decision time, meaning after X number of minutes, I will make a decision how I change the traffic light patterns. So X will be 2, 3, 4, and 6. And as I mentioned, I'm changing the duration of the green, yellow, and red. And I have 20 dynamic traffic light scenarios and 1 static. This is basically the same. Okay, so here are some results that I think may be interesting. The green and the yellow is for the static. The green is for the static throughput, and the yellow is for the static time. So you can think of it anytime, and the red is for the digital twin throughput, and the blue is for the digital twin time. So anytime the digital twin throughput is higher than the static throughput, it's better. I'm getting better too. And this is at 2 minutes decision time. And anytime the digital twin time is less than the static time, it should be better. So my throughput should be higher, and the time to move through the intersection should be lower. So at 2 minutes, it seems to outperform the static situation. So if you look at 3 minutes, this is worse, right? My throughput went down, but my average travel time went down. This is better. Throughput should be higher, traffic time should be lower. If you look at 6 minutes, when I make my decision time at 6 minutes, the throughput went up, travel time is the same. So this is just analyzing video 1. I have another video 1 with different decision times. I have 2 minutes and 4 minutes. The throughput went down, this is worse. The travel time went down, this is better. At 4 minutes, the throughput went up, travel time went up. This is worse, but this is better. Then I analyze the second video. If you look at it, this throughput went down, this is worse. The travel time went down, this is better. This throughput went up, travel time went down, this is better at 4 minutes. Okay, I have video 2, same, throughput went up, travel time went down, this is good. At 2 minute decision time. So you can see these results. Now, I want to take some time to get through. I mentioned that the best case predictive results. What do I mean? I mean that once I look at a 2 minute video or 3 minute video or 4 minute video decision times, I will run that same simulation again with the best traffic settings. So this is the best that I can possibly hope for. This is the theoretical limit. So at 1 minute, you can see the throughput is going up. Average travel time to move through the intersection or specified region went down. This throughput went up, travel time went down, throughput went up, travel time went down, throughput went up, travel time went down, throughput went up, travel time went down. Again, if I know what the traffic looks like, I can make the best traffic light scenarios, right? That's what I'm claiming here. Okay, that's video 1, and this is video 2. Same results. Throughput went up, travel time goes down, so you can see all the way through. So this leaves me to the foundation of for next year, what I can do is I can have a predictive model, AI predictive model, to try to predict the traffic. And if I'm pretty good at predicting the traffic, what it looks like, then I'm hoping that I can get some results similar to these. But I think it wouldn't be as good as these. So that's the approach. And I have a third video, same results. It's belaboring the point. My throughputs are going up, my travel time is going down because I know what the traffic looks like, and I'm setting the traffic lights to the best scenario. That's why I'm getting these results. I hope it makes some sense. So the conclusion is that my digital twin leverages roadside camera data and YOLO for real-time vehicle detection. I'm kind of claiming that I'm using a digital twin built with the SUMO simulator, models of actual traffic conditions, and my traffic light settings are optimized reactively, looking at the traffic and setting the traffic lights. So it's not a proactive, it's a reactive approach. And the traffic light settings are optimized reactively for each time window. Evaluations using real-time traffic showed notable improvements in throughput, especially the 4 minute, and based upon the best traffic, best case scenarios, I show proactive control using traffic prediction models for even better performance. So this work was provided under the direction of Dr. Neon Zing. He's one of my professors at the university, and it was provided by the National Science Foundation. Any questions?